Okay, before trying to explain the Young's double slit experiment in detail, well, why not do it by ourselves using another simulated experiment? And here, in fact, instead of using the light going through two slits, we will try to use two light sources. And as long as they produce light in phase with each other, the result will be exactly the same as the case of double slit case. Okay, so let's do that. Okay, so here we have prepared two light sources, and now the wavelength is adjusted so that the color will be about green. Okay, so let's turn the lights on and see. You can see that the waves are produced, and on the screen, okay, the pattern starts to appear, and you can see there are three bright spots with dark spots in between. Okay, and then you can also take a look at the graph. Okay, so there are three very clear parts of bright signal, and in between there are dark parts. Okay, so now it gives you an idea that when these light waves actually make a constructive interference, you get bright spots here and there, and then when they make destructive interference, then you get dark spots here. Okay, and then let's make some changes. Now remember, we have three bright spots here within the distance given here, and then now let's try to change the spacing between these two light sources. Right now we are at about 2000. I will increase it by 50% so that now the spacing will be about 3000. Okay, and then things are starting to change. Okay, you can clearly see something's changing. And then how many bright spots do you see? Now you see clearly 5 bright spots, which means that the distance between the bright spots have become shorter. So what it already tells us is that if you make the distance between these two light sources larger, then the distance between the bright spots will become smaller. Okay, that's the one thing you have to remember. And then now this time I will change the wavelengths. I will change the wavelengths, which means that I will change the color from green to very dark red, which means that the wavelengths will become longer. Okay, so then let's see what's going to happen. Right now, maintaining the distance between the two light sources, we are seeing 5 these bright patterns, and then I will switch to dark red, which has a much longer wavelength. As you can see, the green pattern has disappeared, and then you see the red parts start to appear. Right now, how many bright parts do you see? Actually, I will try to increase the amplitude and make it clearer. As you can see, there are 1, 2, 3, and maybe half here and half here. So overall, you see 4 bright parts, which is smaller than 5, which we have seen before. So we have increased the wavelengths, and finally, what we have is the increased distance between the bright parts. Okay. So this is what you have to remember, and then we will try to explain these observations quantitatively. Okay. Alright, so here we will try to understand Young's double slit experiment in detail using a theory. Okay, so this is how he set up the experiment. Instead of using the laser, he prepared this light with single wavelengths and then let it pass through a small opening. And according to Huygens principle, it will create spherical wavelets like this. And then on the second screen, there will be 2 slits at the same distance from the original opening, right? So then, of course, the light going through these 2 slits will again be in phase with each other. Okay, and then again, following the Huygens principle, each of them will create spherical wavelets. So on the final screen, they come together, and you will see the repeating patterns of bright and dark spots like this. Okay, so what we want to know is that where does this bright spot and dark spots appear? Okay, and for example, on this position, the light would have been traveled this path from the upper slit, and from the lower slit it would have traveled like this and then finally merge at this position. So you can see the triangular shape like this. So let's try to redraw it so that it looks better here. And then here we want to do the calculation. So therefore let's define some numbers. Okay, so the distance between these two slits, let's call it D. And then the distance between the slit and the screen, let's call it L. And also we have to define the position of this point where these two light waves merge. But instead of defining this position with respect to the center, let's define angle. So angle between two lines. The first line actually connecting the midpoint between two slits and the actual position where lights merge. So it will be this line. And then the second line is actually going straight into the central position, this position. So let's call this angle theta. Okay. So you can simply see that tangent of this angle theta will be L divided by this distance. So here actually it's better to use the angle instead of this distance. Okay. So here when these two light waves merge here, their amplitude of the superposed wave will depend on their phase. And then originally these two lights have the same phase and also the same wavelengths, so therefore their phase depends on the difference between the lengths of these two lines, which is R1 and R2. So and this triangular shape is what we have seen in the previous simulated experiment, and of course we can do the calculation using this triangular shape, but let's make it simpler. We will assume one thing and make this mathematics a lot more simpler. Here what we are going to assume is that L is much larger than D, which means that the slits are very close to each other so that it looks maybe barely visible with eye, but the distance between the slit and the screen is much larger. So if you assume that, then these two lines will become almost parallel, right? They are not exactly parallel, but we can assume they are almost parallel because this distance L is much larger compared to this distance D. So in that case, we can redraw this part over here. So these two lines will look almost parallel, and eventually they merge far away at the position. So therefore, the distance, the difference between the lengths of these two lines will be simply this much. If you draw a line which is going perpendicular to these both lines, right? Okay. In this situation, what we need to find out is this delta x. And again, this was D, which was the distance between two slits. And then we defined the angle theta to be here. But it is easy to figure out that the angle between the line connecting two slits and then and this perpendicular line is also theta, right? Okay, so if you have realized that, now you can see sine of this angle theta is equal to this sine of this angle theta is delta x divided by D. So therefore you can write that now delta x is equal to D multiplied by sine theta. And then finally what we want to find out is where the bright light appear and where the dark light appear. Bright light will be the case when these two light waves are exactly matching in phase. So therefore, if this path difference is exactly 0 or lambda or twice lambda and 3 times lambda, that will be the condition for the constructive interference, and the bright bands will appear. So we can write the final solution in this way: d sine theta is equal to m lambda, and m will be any integer. Okay. And then how about the dark spots? Dark spots, the same length difference will be exactly half lambda different, or in phase it will be pi different or 180 degree difference. That is the condition for the dark band, which means the destructive interference. So we can use the same path difference, which is d sine theta, but not now it is different by half of the lambda, or 1 plus half of the lambda, or 2 plus half of the lambda. They will all equally work. So now you can write the condition for the destructive interference, and the condition for M is all the same. Alright? Alright, so then now we will also want to think about the intensity of the light, which is observed on the screen in the double slit experiment. Okay, and in order to do that, we will use the phasors. Okay, do you remember phasors? Phasors was useful when you are trying to explain the alternating current in the RLC circuit, right? I hope you remember it. So these are the phasors. Okay, so here these arrows, which is just like vectors, now will rotate counterclockwise depending on as the time passes, and then what we actually observe as a wave will be the component projected on the vertical axis. So and then it corresponds to the sine component of this phasor with this the angle will be this phase angle. Okay, and then now we have two arrows because there are two slits, and the light will pass through these two slits and arrive at the same position. But when they arrive, of course, first thing we have to know is that they will rotate at the same angular frequency, but they are at the different phase angle, right? Because they have traveled different paths. So now we can write the first wave as the E0 multiplied by sine omega t. E0 will be the amplitude of the original light, which is actually an electric field. And the second wave will be E0 multiplied by sine omega t plus phi. So they rotate at the same angular speed, angular velocity, or angular frequency. So this omega t actually doesn't matter, but what is important is this phi, which is the phase difference between these two waves. Okay, and finally what we want to do is we want to make a summation between these two. Okay, and so one thing we have to check is that in the previous slide we learned that for the intensity maxima, d sine theta is equal to m lambda, and at the same time one wavelength corresponds to 2 pi in angle or phase, right? So therefore for intensity maxima, the path difference was integer multiple of the wavelengths, so therefore the phase difference will be integer multiple of 2 pi, right? So then by combining these two equations, now you can drop m, and actually this m came from the intensity maxima, and then now we are dropping this m, so therefore this equation which we obtained by combining these two this equation does not only apply to the intensity maxima, but it also applies to intensity minima, and actually it applies to any phase angle. Okay, so this is an important thing. You have to remember this relation, which is a relation between this phase difference and the actual angle where it's observed is good in any position on the screen. Okay, so eventually what we want to do is that we want to make a summation between these two phasors, which are at the phase difference phi, and then it will look like this. Okay, so phasors are just like vectors, so you can move the second phasor to this position and make a summation. Then this big blue arrow will be the new phasor, which is the summation between the two original phasors. So as time goes on, this big arrow will rotate, and then we will see the sine wave which is projected on the vertical axis. That's the total wave we will be observing, and actual intensity is, of course, intensity is square of this, but probably you will continue to observe bright spots if the condition is satisfied. So what we are doing is the summation, which is the summation between E1 and E2, and in fact, according to this phasor diagram, now you see that the size of this total wave will be, using simple geometry, is twice, actually, okay, twice comes from this. Now this 2 times this phasor length multiplied by cosine of, say, this angle, which is half angle, and then this angle is actually beta, and this is half of the phi, and finally we can write that the total length of this phasor will be twice the E0 multiplied by cosine half of the phase angle. Okay, so do you get that? And then finally what we want to know is that what will be the intensity at certain position with respect to the original intensity I0. So intensity ratio is equals to the ratio between the square of the amplitude, of course, and then now we see that actually E0 here square will drop with this guy, and what is only remaining is 4 times the cosine square of this phase. Okay, so what it means is that now intensity will look like a cosine square function with respect to the phase angle. So cosine square will oscillate between, say, 0 and 1. So 0 will be the position of the dark intensity, dark spot, and the 1 will be the position of the bright spot or maximum intensity, and it will oscillate like this. And in this graph, actually this axis is actually the phase. So what is actually phase? Phase actually, in this case, if you try to write using this equation again, phase is actually directly proportional to the sine theta. Sine theta is of course the angle, and we learned that actually if you convert this to tangent theta, this is also directly proportional to the position on the screen. So therefore here this axis is like sine theta, sine theta, which is nearly proportional to tangent theta as long as the angle is not very big. And then of course this is again proportional to the position on the screen. Okay, so what is important here is that when you have the intensity of the light coming through this double slit, it will oscillate like a cosine square function, and as you can see, it will cosine square function will go on forever. So however far away you go from the center, it will always have the cosine square function. Okay.